So, in the last lecture we have seen we have introduced the concept of stresses and how we need to have two indices for this, and we also identified what are the stress components acting in the x direction in a cubical box like control volume, and the idea of this is to see how these stresses acting in the direction will contribute to change in the rate of change of linear momentum. So, we are going to do that. This is our box here, and we identified the 6 stress components acting in the x direction on each of the 6 faces, and they are whether in which direction they are acting in x, whether in the positive x direction or negative x direction, depends on whether it is a negative phase or a positive phase, as explained previously, and that is also marked here. So, now we would like to multiply each stress component by the corresponding area here. So, if we say that what is the net force acting in the x direction from the stress which is acting on this positive phase, this will be given by sigma xx at x plus delta x times the area of this phase, which is delta y times delta z. Similarly, the stress which is acting in the negative x direction by the stress acting on the left phase will be sigma xx at x times delta z times delta y, but it is negative. So, this is minus delta x like this. Now, if you look at the top face, the area of the top face is delta z delta x times sigma yx at y plus delta y, and that is acting in the positive x direction. And the bottom face, again you have the same area delta z delta x times minus sigma yx at y, minus because it is acting in the negative direction. So, we can write down the external forces, sum of net external forces on the control volume due to stresses acting on the outer faces, enveloping faces of this control volume, stresses in the x direction only because only the any force acting in the x direction will lead to change in the linear momentum in the x direction, which is what we are considering. So, we can say that this is equal to sigma xx at x plus delta x times the area, which is delta y delta z, minus sigma xx at delta y delta z at x plus sigma yx at y plus delta y times the area minus sigma yx times the area by y, like this. So, we have here a mathematical expression for the sum of net external forces, and we have this component from the net external body force, and then we have expressions here for net momentum flow rate in, net momentum flow rate out, and the rate of accumulation of x momentum. So, all this can be substituted here and we can get an overall expression. Okay. So, that overall expression is like what we have seen, it will have the delta y delta x delta z, and we do the same thing as what we have done before. We divide all the terms by delta y delta x delta z and take the limit as delta x tends to 0, delta y tends to 0, and delta z tends to 0, and that will give us, this particular thing will give us dou by dou t of rho u. Okay. Now, you have to this is plus and this is minus because this is entering and this is leaving. If you consider only these two terms here, and if you divide everything by delta x delta y delta z, then this delta y delta z will cancel out, and these two will give us rho u at x. When we say rho u, it is equal to rho u square because these are velocity components, scalars. So, we can multiply by that. So, we can get rho u square at x minus rho u square at x plus delta x divided by the delta x which remains from division by the delta x delta y delta z in the limit as delta x tends to 0, and that is equal to minus dou by dou x of rho u square, and because that is on the other side of the equal to thing, we bring it to the left hand side, you get dou by dou x of rho u square. Similarly, these two when divide by delta x, delta y, delta z, and then we have delta y remains in the denominator, we take the limit as delta y tends to 0, those two will give us minus dou by dou y of rho u v, and when we bring it to the left hand side we get dou by dou y of rho u v, and we get this from the net momentum flow rate that is coming in is given by dou by dou x, dou by dou z of rho u v. So, these are the net momentum flow rate, x momentum flow rate in when they are on the left hand side, on the when they are on the right hand side. On this left hand side when they are brought in, so this is the net x momentum flow rate out of the control volume. Okay. Now, you take these two things and then you divide by delta x, delta y, delta z, and take the limit as delta x tends to 0. That gives us rho xx at x plus delta x minus rho xs at x divided by delta x as delta x tends to 0. You get dou by dou x of sigma xx. These two will give us dou by dou y of sigma yx. Why is it dou by dou y? Because when we divide these two terms by delta x, delta y, delta z, delta x, delta z cancel out and only delta y remains in the denominator. So, when you take in the limit of delta x tends to 0, delta y tends to 0, delta z tends to 0, as you take the limit as delta y tends to 0, this becomes a partial derivative dou by dou y of sigma yx, and similarly this will give us dou by dou z of sigma zx, and you have divide by this by delta x, delta z, you get rho gx. So, this is our momentum balance equation. Okay. So, we have got a mathematical statement for the conservation of mass conservation, which is like this, and we have got a conservation of a momentum equation here. Similarly, we can write the conservation of, this is the conservation of momentum in the x direction, where F is the body force per unit volume, and the y direction conservation momentum is very similar. Since we are dealing with x momentum, we get u component here. This is the momentum conservation in the y direction, so that gives us v here, and one of the u's becomes v here, and so this u becomes v, so this u becomes v here, and this u becomes v here, so you have this. And similarly, when you consider the z momentum balance, this v becomes w, one of the v's becomes w here, and one of the, this v becomes w here, so you get rho w square. So, these are all the rate of change, the temporal change here, and then the change associated with the flow, that is the difference between what is coming in with the flow and what is going out with the flow is advection. This is called the advection term here, and then the body force term, and then these are the stresses acting on this. So, using index notation, we can write in a short form like this: dou by dou t of rho u I plus dou by dou x j of u I u j equal to dou by dou x j of sigma j I equal to rho g I. Now, here in this term we have one repeated index. So, there are 3 terms, but they are not summed, okay, because it is not a repeated index. So, there are 3 individual terms, and therefore, this is representing 3 equations, this equation, this equation, this equation. Okay. In this term here, there are 2 indices I and j, and only j is being repeated. So, that means that in this term is actually a sum of 3 terms, in which j can take the value of 1 and 2, 1, 2, 3, but I remains the same. So, what is the value of I? That is defined by this term here. If I equal to 1 here, it is also equal to 1 here. So, when you put I equal to 1, you are looking at momentum conservation in the x direction. When you put I equal to 2, you are talking about momentum conservation in the y direction and z direction for I equal to 3. So, now if you consider, for example, I equal to 2, so that is momentum conservation in the y direction. So, u2 is v. Okay. So, this term here represents dou by dou xj of rho v times uj, and when this implies sum over three numbers j equal to 1, 2, 3. So, when you put j equal to 1 you get u here and x. So, that is rho uv by dou x. When you put j equal to 2 you get u2 is v and then x2 is y. So, you have this, and that v multiplies here to give you v square. When you put j equal to 3 here you get x3 is z and then u3 is w, you get this. In all the cases u2 has that is equal to v, which has remained the same. So, one part of this is remaining the same even here, and the other things are changing because j is a repeated index and I is not a repeated index. Now, when you come to this again, here in this short term there are two indices here and one index here, and it is being repeated over j here, and what is not changing is the second index I. Why is it so? If you consider these three terms here, in this x the second index is unchanging, only x, y, z, the first index is changing, taking the values of x, y, z here. So, when you consider the x momentum equation, then I is not changing. So, the direction representing the force acting is not changing. So, that is why you put I index here and j index here. And we would like to point out at this stage that in a term like this, if there is a repeated index, that j is a dummy index. So, it does not matter whether it is j or k or m, it gets washed out when you expand this, but this index remains the same. So, for example, when you put I equal to 1, this has to be x here, and it is the same, the corresponding x component in x component. So, that I identity is maintained throughout here, but whether it is j or k, it does not matter because it is anyway going to be x, y, it is going to change x, y, z like this. So, the j here is a dummy index and I is a proper index with substance attached to it. So, sometimes for convenience we put it as dou by dou x m of rho m I, it is the same as dou by dou x j of rho j I. Okay. So, this is a conservation of linear momentum, but we have a problem because the conservation of linear momentum in itself given like that is not very useful, because if you are considering a flow in which there is no heat transfer, just air flowing over a car, okay, you are not really interested in the temperature, you are not interested in any kind of reaction that may be happening and all that. So, you should say that this should be given only by the mass conservation and momentum conservation. Okay. So, if you do that, then the number of equations that you have are 4, because you have one continuity equation or the mass conservation equation and 3 momentum conservation equation in the x direction, y direction, z direction. So, you have 4 equations, and how many variables are there? Here you have 3 variables because u is uvw. If you look at this set of equation and the continuity equation here, in the continuity equation you have rho uvw. Okay, you can say rho is the density of the fluid and I should know it. So, you could say that or it is given independently, and so you have 3 variables uvw here, and in these 3 equations you have uvw. So, good, but on this side fb is not known, and we can say that we are only considering gravity, and we know the g, gravitational constant, is known, and we know the direction of the components because we are aligning, it depends on what control volume we choose. Once we choose the control volume, then the gx, gy, gz are known. So, you can say that as long as we restrict ourselves to gravitational component alone, then this is known, you already have uvw here, but these stresses, there are 9 of these are also not known, and we are looking at gradients. So, that means that we are saying that these stresses can change with position. So, that means that these are variables. So, when you look at the number of variables that are present in these 4 equations, these are UVW and the 9 stress components. So, you have 13 variables and you have only 4 equations, okay, and you are looking at a flow without heat transfer and all that, and you do not see why you have to consider energy equation and all that. Okay. So, in that sense you have a problem because you have an indeterminate system. You have too few equations and too many unknowns, and that gives us a problem here. So, you can try to bring in other equations. You can say what I have considered is linear momentum, but I can also conserve angular momentum, and that has nothing to do with heat transfer and all that. So, I can invoke the angular momentum balance equation. You could do that, and if you apply it and go through it systematically, it gives you extra relations. It tells you that the stresses that we are considering here must be symmetric. So, that means that sigma ij must be equal to sigma ji. So, that means that sigma xy is equal to sigma yx, sigma yz is equal to sigma zy, and sigma xz equal to sigma zx. This is useful because instead of the 9 components that you have here, there are only 6 independent components, because if you know sigma yx, then sigma xy is known. So, you can substitute here, you can eliminate sigma xy and just keep sigma yx here. So, you have 6 components here. Okay. So, in that sense angular momentum conservation is good, but it does not solve the problem because we still have too many unknowns. You have UVW and 6 stress components and too few equations, only 4, one continuity equation or the mass conservation equation and the 3 linear momentum balance equations. We have already used the angular momentum balance equation, there is nothing more to get from it. Okay. So, this means that we have a system of equations here which does not lead us to a useful solution because we have too many unknowns. So, we need to bring in, there is no way out because we cannot think of any other relevant fundamental laws that need to be obeyed by this. Okay. So, we need to bring in additional empiricism, more about the nature of the fluid that needs to be brought down to close this system of equations. And so, this is where we look at the analogy with solid mechanics, where when we are considering forces and displacements and deformations and all that, we bring in the Hooke's law of elasticity, where the stress is made proportional to the strain. For example, if you imagine a spring and then you stretch it, and the amount of stretch, the strain that is produced in the spring is proportional to the stress that you apply, and that is a Hooke's law. Okay. So, there you have a relation, an empirical relation, because it is not always correct, and it is more, it is a law which is obeyed by many solid substances under certain limiting but still useful conditions. So, we take that Hooke's law as a useful gift to us so that we can continue with our analysis. So, we take that Hooke's law of elasticity, and we would say that here we are talking about stresses, and we should somehow then be able to make use of a similar kind of, that is what Newton's law of viscosity says. You have the viscosity as a special property of the fluid, and we know that based on observation that you have viscosity resists this deformation. So, you can bring in a similar law in which the stress induced to fluid motion is proportional to the strain rate. Okay. So, stress induced by fluid motion is proportional to the rate of strain rather than strain. So, we can make an assumption like this, and we will, in order to truly understand this, we need to study the kinematics of fluid motion. So, this is what we will do in the next lecture. We will what we have done in this lecture, in this short lecture, is to pose this conservation of linear momentum in verbal statement, and we have worked out what each of those terms are, and based on these terms we have been able to come up with a conservation of linear momentum principle, but we find that it is not sufficient enough, and we therefore pose the angular momentum principle, and we have reduced the number of unknowns, but we still do not have enough. So, we are now trying to pose an empirical, bring in an empirical relation. This empirical relation has to be brought in a proper way, so that it is applicable in the general case, not in the specific case. So, that is what we are going to do in the next lecture.